When you strip away the physical world, how do mathematicians measure the distance between abstract concepts? In Walter Rudin's Principles of Mathematical Analysis, the answer lies in understanding metric spaces. Up until now, you've likely relied on the standard absolute value on a real number line. That works for basic points, but once we start comparing entire sequences, vectors, or infinite functions, that simple geometric ruler breaks down. We need a more universal tool. To build that tool, we have to let go of our standard geometric intuition. We take away the axes, the coordinates, and the grid lines, leaving behind only the pure relational distance between 2 points, which we denote as d of pq. Freeing distance from a physical coordinate system is the necessary first step to defining the formal rules for convergence and continuity in higher-level analysis. This block of text is definition 2.15, straight from Rudin's book. It serves as the formal blueprint for our universal mathematical ruler, laying out 3 strict axioms for what qualifies as a metric space. The first 2 axioms establish the baseline. First is positivity. The distance between any 2 distinct points must be greater than 0. Second is symmetry. Calculating the distance from P to Q will always give you the exact same positive value as swapping directions and measuring from Q back to P. The third rule is the famous triangle inequality. It dictates that taking a detour through any third point, R, will always be longer than, or at best equal to, the direct straight-line path between P and Q. These rules allow for highly unusual spaces, like the discrete metric. In this space, the distance between any 2 distinct points is statically locked at exactly 1. Even here, if you test any 3 points, you'll find the triangle inequality perfectly holds up. A valid metric space doesn't need to look like a continuous physical shape. It solely needs to obey these 3 logical axioms without fail. Looking closely at definition 2.18, we are immediately hit with a dense block of 10 abstract topological terms. Processing all of this text simultaneously is notoriously difficult. The neighborhood serves as the geometric foundation for these terms. It is defined as an open ball of a specific radius centered around a point P inside our set. We use this neighborhood bubble to categorize points. If we can draw that circular neighborhood so it fits cleanly inside the set's boundaries, we classify P as an interior point. But watch what happens when we move toward the edge. If the point sits precisely on the boundary, its neighborhood inevitably leaks outside the shaded set. This makes it a limit point. With those categories established, an open set is straightforward. A set is open if it is composed entirely of interior points, containing 0 boundary limit points. Whether a space is open, closed, or dense, all of these complex topological structures are built entirely from the simple geometric behaviors defined by our initial distance metric. We can test these definitions by examining Theorem 2.19, which states that every neighborhood is itself an open set. The algebra in this proof relies directly on the triangle inequality. Let's visualize the objective. We start with a large neighborhood around point P, and we pick a random point Q somewhere inside it. To prove this set is open, we have to show Q can have its own safe neighborhood that doesn't breach the outer wall. The challenge is calculating the exact maximum radius for point Q's new neighborhood. By taking the total radius r and subtracting the distance h between our 2 points, we get a precise remainder, r minus h. We set Q's radius to that exact remainder. The triangle inequality guarantees that this new, smaller circle will fit securely inside the larger one, proving that Q is an interior point. Mastering this specific geometric subtraction provides the logical template used to solve many of the fundamental proof patterns found in undergraduate real analysis. These definitions provide the foundation for compactness, a property that allows us to generalize the behavior of closed and bounded intervals to more abstract spaces. Metric spaces elevate raw, unstructured sets by giving them a rigid, logical framework. By clearly defining distance, we define the shape and rules of the entire space. Here is a visual cheat sheet connecting today's logic chain. Take a screenshot for your notes. It maps the direct path from the 3 metric properties all the way to the definition of an open set. Deconstructing dense text like Rudin step-by-step makes higher mathematics accessible. Subscribe to the channel for the upcoming breakdown on compactness, and I'll see you in the next video.